Okay, I will start the lesson, the last lesson for our semester, linear regression. And I will not go very deep into linear regression in your final. Even though I believe my lecture, I try to go in depth, but for the question for your final should be simple. Okay, I will give you data given paired data set. The question will be first find linear regression equation. Linear regression equation, and then second find a correlation coefficient that's dr. A linear regression equation is y hat equals to ax plus b. And then the third thing is find the coefficient of determination r squared. And all these three numbers actually are from your calculator. Okay, and then the fourth one is find the residual from a data point. Okay, but all the theoretical foundation, I believe, was well given in the lecture. So what we do right now is just another example of how to use calculator to get these three informations here, and how to compute the residual from a data point. And that's all I will ask you in your final. Okay, that's all I will ask you in your final. You should think of that as an extra credit. Okay, let me go on. An example from number 14. This is number 14, which chapter? Let me see. This is chapter 10, section 2, I believe. Chapter 10, section 2. Chapter 10, section 2, number 14. So using the listed duration and interval after times, find the best predicted interval after time for an eruption with a duration 253. So basically, for the Yellowstone geyser, is it? And suppose in the duration of the eruption is 242 seconds, then how many minutes after that will the next eruption happen? Okay, how many minutes after that will, so suppose right now the duration of the eruption is 242 seconds, and they found out that the interval after that duration, after that eruption, 91 minutes after that, then they have the next eruption. Okay, now then the question is, can we use the duration of the previous or the last eruption to predict when is the next eruption? Okay, now that's what we want to do. Now, this is how we will do it. We will use calculator. We'll use calculator. So grab your calculator. We will insert data. We will input data. And the way we input that will be the same to when we input the data for match pair. Okay, we go to stats. Let's see. I think I have list 1, 2 here. Okay, so let me clear that first. List 1, comma, list 2. I clear them. Okay, now let's see. Now they are clean, right? Okay, now then L1, you plug in the first row, 242, 255, 227, 251, 262, 207, 140. Okay, there are seven data points, and then let's see the pair. The next eruption happens 91 minutes after, 81 minutes after, 91 minutes after, 92 minutes after, 102 minutes after, 94 minutes after, and then 91 minutes after. Okay, so we already input the data. Now then, where do we find the linear regression line? Okay, you go to stat, okay, and then calculate. Number 4, linear regression, ax plus b. Okay, so you go to, and then your x list 1, and then list 2 already there. Okay, and then calculate. Ding. This is the result. Okay, so how do you punch it? Calculator. After inputting data, input the data, you go to stat, calculate, and then you go to what's that? Lin rec, ax plus b. Now there's a chance that your calculator is not properly set up such that you only see the a and b, the first 3 rows here, and you don't get the r square, you don't get the r. Now if that's the case, then you go to mode, go down very, very far to the bottom, then you will see the stats diagnostic. Now there's a chance the reason it doesn't show up the R and R squared because your stats diagnostic still off. Let me show you what happens if this is off. If this is off, okay, then you go to stats, calculate, lin rec. It will only show up the A and B, right? So you need to change that. You go to mode, okay, you go to stat diagnostic, okay, turn it on. Okay, turn it on. Then you go to stats, calculate, lin rec. List 1 is for the X list, list Y list, that's list 2, and then so on and so forth. Okay, that's how we get this. Now, let's go back here. So, suppose I give you this information. Then my first question will be, what, or find the linear regression equation. Find the linear regression equation. And that will be y hat, because that's a prediction, equals to ax plus b according to this. Okay, ax plus b. What is the a? The a is 0.001. 0.00673, and then x plus b, which is 90.19027. Okay, that's the linear regression equation. Now, how about the correlation coefficient? Correlation coefficient, that's the R, which is 0.04658. Yeah, if the R is this small, then it's basically no correlation between the duration of the previous eruption to the interval to the next eruption, time interval to the next eruption. There's if this is the R is so small. Okay, and then coefficient of determination. The coefficient of determination is the R squared, which is 0.00215. Basically, this coefficient of determination says the following. Only approximately, it's only 0.2% of the interval to the next eruption is determined by the duration of the previous eruption. Okay, only 0.2%. Basically, they are saying that now there's no correlation. Knowing the duration of the previous eruption does not tell us how long we need to wait to the next eruption. That's basically what the conclusion we will make later on, if the coefficient of determination is that low. Okay, now once we see that the coefficient of determination is less than 70%, usually then we don't go on to the next step. The next step is, if we want to use this line as this regression line as a predictor, then find the residual for let's say 227 seconds. Suppose the previous eruption is 227 seconds. Okay, now the wait time after that is 91 minutes, right? Okay, that's the data point. Okay, what is the residual? Then the residual is the difference between the actual outcome minus the predicted outcome. That's residual. Okay, but again, it is actually not appropriate to ask the residual once we have such a low coefficient of determination. What I do here, just an example, what we do if what we need to show, what we do if that's the question. If we really need to find the residual, how we do it. Okay, so the Y is 91 minutes. The Y is 91 minutes. Now, how about the Y hat? Y hat is the predicted waiting time to the next eruption. Okay, if the previous eruption is 227 seconds, that will be 0.00673 times 227 plus 90.19027. That's the Y bar, Y hat. Now let me plug in the numbers. 0.00673 times 227 plus 90.19027. So the prediction is Y hat equals to 91.71798 minutes. Okay, So the residual is the actual minutes, which is 91, minus the predicted minutes. That is negative 0.71798. And that's it. That's it. Okay, that's it. Okay, as you can see, because of the complexity of the data here, the complexity of the computation, I will just teach you how to use calculator, and I don't have time to go further than the lecture that I gave you. Okay, when is it appropriate to use linear regression, for example? Okay, like we need to actually do a hypothesis testing if the coefficient of correlation, the R, is big enough. Like, is it close to +1? Is it close to -1? Okay, is there any correlation to start with? Okay, we're supposed to do hypothesis testing for that. And we also need to make sure that the data is actually not, for example, not other type. We should make sure that it is actually linear corresponding related linearly. Like if one of them increase, the other one increases also. And it doesn't form a quadratic or periodical pattern. Okay, so it's actually quite strict on when we're supposed to use this, when not to use it. Okay, now the thing is, let me warn you ahead that there have been situations that I see recently where the context was actually not linear, yet some scientists, they call themselves scientists, but they don't learn their statistic well. They apply linear regression. For example, the temperature on the first couple of months of the year. Okay, this is just an example. Okay, an illustration. What kind of mistake they make? For example, you cannot use the temperature in the first couple of months of the year. We know in January, February, and March, we know it's on the cooler side and it tends to be warmer over time, right? Okay, but we also know that the temperature along the year is actually increasing in the summer and then going down again in October, November, December, right? That's what we know the pattern. Okay, now the thing is, you cannot just use the temperature of the first couple months, like every days on the first couple months, and use that to extrapolate what happened in October, December, thinking they will be increasing linearly. That's not right. That's not right. Trust me, your prediction will be so wrong. Okay, that's one. Another one is, for example, how tall your teen's supposed to be. Okay, suppose you try to line them up according to the age. Like you think like 5 years old, 6 years old, 7 years old, 8 years old, 9 years old, 10 years old. You see that the graphic is increasing, which supposed to be, they're supposed to get taller, right? Children's supposed to get taller. But we know over time that the increase actually getting slower. Once you reach like around 30, 40 years old, your height is basically constant. Okay, your height basically constant. And then after you are like 60, 70 years old, then you actually get shorter. Well, I mean, that's the fact, right? That's a fact. Now, so what is wrong is when you use the informations from the first couple, let's say 10 years of our lives, and then use that to predict how tall you will be when you are 80 years old. Now, that's not appropriate. Okay, that's not appropriate. That's what we call extrapolation. Even if you want to extrapolate like outside of the interval of your own data, let's say you use data up to 11 years old only. Okay, then I think it's still reasonable to talk about how tall we expect that person to be when he or she is 12 years old or 13 years old. I think it's still okay. We can use it, right? Okay, but not 80 years old. We know that's not true. Okay, using the data you have here, your data becomes irrelevant for those people who are 80 years old. And you will be surprised at how off your data is. Now, the thing is, it is being used by those people who claim themselves to be scientists, but they don't learn statistics well. Okay. Now, unfortunately, because they are scientists, okay, they may be good in their chemistry, but then they're enough to use statistics in which you are not an expert. Okay. And whoever listen to them will just believe what they say. Why? In the name of being the expert of, for example, chemistry. No offense to chemistry people. Okay, like I should not talk. My expertise in statistics. I should not talk about chemistry as if I were the expert there, an expert there. No. Likewise, if there are chemists in chemistry major, in physics field, okay, they should learn statistics before talk in sense of statistics. That's what I'm saying. Okay, that's what I'm saying. Which is not the case recently. Okay, which is not the case recently. I see that a lot, though. I see that a lot. To the point that even though you put it in the news about some statistic result, I'm to the point that I don't believe them anymore. You know, I don't believe them anymore. It's like these journalists, they talk about statistics without knowing what they're talking about. Okay. Now that's for one question. Let's do one more question. Let me pick a question from our textbook. Let's see number. Oh, hold on. What is this? No, this is chapter 11 already. No, I don't do chapter 11. Let me go back to chapter 10. Why suddenly jump to chapter 11? And I'm not doing multiple regression either. There's something called nonlinear regression. So that's why. That's why. Don't just apply linear regression. I need to go back quite far. That's 10.2. And it's a lot of use of calculator. That's why I cannot go too far. Give me a second. I'm almost there. Okay, let's do number 25. Let's do my number 25. This is especially relevant to those students who work as whose income, part of income actually based on tips. Okay, so do we have a reason to be happier if a big group of customers coming to our restaurant, for example? Okay, now using the bill or tip data, find the best predicted tip amount for a diner bill of 100. So using this data, what can you say about the expected tip for a bill of 100? Okay, let's plug in the data. So I will clean up my list again. Clear list 1 and list 2. Clear list 1, comma, list 2. Go to stats, edit. Now I will enter for the first column, the bill 33.46. Sorry, wrong place. I want to clear that. This 33.46 50.46, 50.68, 87.92, 98.84, 63.6, 107.34. So using only 6 data here, can we say something about to use that to predict? Okay, so I already input all the informations here. Check again, just in case you have any typo. Okay, now then, if everything correct, you go to stats, calculate, linear regression. There are actually 2 linear regression. I think if you go down further, there's another linear regression. But this linear regression here, A is the constant, B is the coefficient of X. The one we have in number 4 linear regression, where A is the coefficient of X and B is the constant. So you can use either one actually. Okay, and then calculate. Doom. Let me screenshot that here so that I don't need to go back to my calculator again and again. Okay, now this is the result. Okay, so in your test, all I need you to do is, if I ask you what is the linear regression equation, so you will say y hat, don't forget the hat because you use this as a prediction. The A is 0.14861x plus the B is negative 0.347228. And then part B, what is the R? What is the R? This is the correlation coefficient. Correlation coefficient. As if the correlation coefficient is positive, then as one variable increases, the other variable also increases. Okay, and R squared, which is coefficient of determination, coefficient of determination, you see that's equals to 0.68585. Now this tells us that approximately 68.585% of the tip is actually depends on the bill. Okay, we know it depends on the surface also, right? Okay, if the customer thinks that our service is good, of course we expect more than this, right? If it's lack of expected service, then our expected tip will be less than the tip we get will be less than what this linear regression predict. Okay. So it does make sense that part of the tip actually depends on how much the bill, but we know that's not the only determination. Okay, so then they come up with this. So suppose if your bill is if X is 100, what is the Y hat? What is the expected tip? Then that will be 0.146861 times 100 minus 0.34728. Okay, so that's 0.14861 times 100 minus 0.34728. That will be y hat will be $14.51372. That's the expected tip. Okay. Hey, by the way, if therefore you're working in the surface industry where your income more or less depends on the tip, then you can use this to actually predict if your service is considered acceptable, above average, or less than expected. Okay, so because hey, if our customers happy with our service, they tend to tip us more, right? And if our service is less than what they would expect, they tend to tip us less. Okay, now so suppose that somebody have a $100 bill, I expect around $14.51 tip. But if that person suddenly give me something a lot bigger than that, let's say $20, then more or less it means that person is happy with our service. But if it is less than 14, let's say $10, $11, $12, then it is a feedback to us that you know what, we are not doing a good job for that person. Okay, we should improve more. Okay, but basically what I want to go over today are these two, and that's what the additional type of question you should expect for next week. Okay. Okay, next week your test will start from 8:20 and you will have 3 hours again for your final. I may give you extra time, but just not a lot though, maybe only 10-15 minutes at most. Okay, see you then next week.